the implementation, it's pretty crappy, right? And it's going to be slow. So that's why we're not going beyond that. But theoretically, if the person was willing to wait long enough, it should be able to solve any size of a matrix. They will always be square matrices, yes. Okay. So let's talk about multi-file projects and why we like to do them. So sometimes your projects get really big and you're going to want to split them up into multiple files. This helps in a lot of different ways. One is like organization, right? You can group code that is similar to each other into a single file, and you know where to go look for that code, right? For example, if you want to do something with input and output, what system library would you look in? stdio.h, right? Or if you're looking for doing something with math, you would look in math.h, right? So you know where to look based on the names instead of having to pour through some gigantic file to find what you want, right? It's also going to be less to look through at once. So it makes things easier. It's also going to make your code more reusable. You can break it up into different libraries and reuse those libraries in different programs, right? For example, we talked about input validation. That might be something that you want to do a lot. So if you just have a file that does all the input validation, you could just include the appropriate header file and then compile with that file, and great, you're done, right? You don't have to keep rewriting things. One second. And then finally, it's also going to potentially reduce the amount of time it takes to compile your program if you break it up into different files, depending on how you specify that you want to compile. It's not plagiarism if you reuse your own code. Oh, I don't know why your professor said that, but like you want to keep building on top of what it is that you've done before, right? If you've solved a similar problem in the past, why not reuse your solution, right? There's no need to reinvent the wheel. This is why it's also like nice to go look online to see if there are libraries of pieces of code that have already solved the problem that you want, right? Here in class, your focus should be on learning, right? And so that's why you maybe sometimes have to reinvent the wheel. But in like when you're actually out in the industry, your first thing to do if you need to solve a problem should be to look to see if somebody's already solved that problem and then use their answer, right? It's the complete opposite of school, right? But it saves you a lot of time if there's already something working there. So when you split up your files, you're going to split them into two files. They're going to be the header files, the .h, and your source files, the .c or .cpp when you get to C++. The header files have all the declarations in them. This includes your struct declarations as well, or your enum declarations. They're all going to go into header files. The C files have the definitions of the code, actually what code should be run. And when you have your user-defined files and you want to include them, you put them inside quotation marks instead of the triangular brackets to include them. I noticed that like instead is spelled wrong. The C file will always include its .h file. So if you have, prog.c is always going to include prog.h. And what does pound include mean? Copy paste, right? We're really just copying and pasting all the declarations into that file. And if other files will eventually need to call some of those functions, they'll also need to include it as well. That's it. So let's say we had some source file, it's basic.c, pound includes stdao, pound includes basic.h, right? Not sure why I included it twice. Then we want to add one and we have a double. So this is our C file, and our H file has the declarations. You're also going to notice the H file has this thing made up of these three lines, the poundif endef, pound define, pound endif. These are called the compiler guards. And what it's doing is it's preventing this code from being re-included twice. So again, anything that starts with a pound sign is a directive to the preprocessor. So what the preprocessor is going to do is going to see, hey, has a symbol called basic_h been defined? If it hasn't, that's the N, not defined, it's going to go and it's actually going to look through the code that's beneath. So we'll define basic underscore h, and then we're going to go put that code down there until the end of the if. So if we include this file once, fine. We're going to get this contents, add one, add, and then the print greeting. But if we can try to include the file a second time, we're going to see that basic underscore h has already been included, so we're not going to copy and paste anything inside of it. This can definitely happen if multiple files, like you include some header file, and then that needs to, like, say, include stdio.h, and then you also need to include stdio.h for your work. It prevents it from being included twice, which prevents the double declaration errors.
First time, and then after.
So it's just going to go through the file in order. So it's like, hey, has basic underscore h not been defined? If it hasn't been defined, we're going to go inside the if statement and define basic underscore h. We'll copy and paste all the other code that's inside here to the end of the if. Once the if somebody else included the file a second time, we would see that this symbol basic underscore h had been defined, and so we would not copy and paste it in. So one of the reasons that you want to include the header file in the C file is the first reason is it lets you define the functions in any order, right? Which is really nice. Again, there's no dependency once you have all the declarations at the top, right? If you didn't include the file, you'd have to be like, make sure that every function is defined before it's called, which is gonna be a big pain in the butt. The other reason is so that the compiler is being consistent and double checking that the declarations match the definitions, right? Because if you have a different definition, like let's say you change your definition inside the .c, but you forgot to change the .h, right? Everyone that's including that .h gets that new declaration, and the definition doesn't match up anymore, so it might not be called correctly anymore, and the compiler can't catch that error as easily because you didn't include the declaration in yourself. So I think you said include the main.c. You would never include the .c files. You only include the .h. But like generally, main should be very short as what it does.
All the other.
So like in terms of breaking it up, it depends on how big your problem is. If you're like doing some small demos like we've been doing in class, I'll put everything in one file. If things are going to be more complex and we need more organization, I'm going to start splitting it up. But generally I have like one file called main.c that has the main function, and it's pretty simple what main does. Generally it might be just a series of function calls or a loop that does some function calls, but not too much more than that. So the compiler does not see any difference between including a header file and C file. Copy paste the contents. It's just in general, if you've included the C file more than once at all, you'll have double definition errors because you've defined the problem multiple times in different files. That's why you don't want to include the .c's, only .h's. So basically the name of the file that you have, all in caps underscore h. So notice the name of the file over here is basic.h. So generally you're going to name the guard file name underscore h, right? The reason to do this is that the guard names need to be unique. And like the best way of guaranteeing that the guard names are unique is that your file names are unique as well. Because I have had students that have issues where they've accidentally named their guards the same, and so like they tried to include the first file and then they include the second file, but the second file is not being included because they had the same guard name. Because one bad thing about CLion is like when you like rename a file in CLion, it will not rename the guard automatically, even though I think it should. So we talked about the guard, talked about that. So if you want to compile multiple files together, it's pretty easy. If you were doing it on the command line, you'd say GCC, and then you list your normal command line options, and then you just specify all the C files you want to compile. It will create an executable. The downside for this is that it can be very time consuming to compile a large project, especially if it's made up of like, hundreds of files, right? Thousands and tens of thousands of lines of code. Compiling the entire thing can take quite a bit of time. This is really annoying if you just change like one line of code in one file and now have to wait minutes to test to see if your code is working. So what we can do is we can partially compile each of the individual .c files into objectfiles.o and then link those .o files together to form our final executable. So now, if we only modify like one .c file, we only have to update that one .o file. And if we modify the .h's, then we're going to have to modify anybody that included that .h. This can be kind of hard to remember how to do, so you can create something called a Makefile that lists out the dependencies there. The syntax is some target, what it depends on, and then what rule that you'd like to run to make that file up to date. If any of the dependencies have been modified since the last time, Make will make sure to re-update them. Blah, blah, blah. First rule should be the name of the executable you want to create. It depends on all of its object files. There's going to be one object file per C file. And each of the object files has the same name, but with .o instead of .c. And then the update rule will be GCC, all the options, the exe name, and then all the .o files. Then for each object file, you're going to have a rule. It will depend on the C file of the same name. It will also depend on the H file of the same name. And it will also depend on any .h files that the .c and the .h include. So here's an example, A.c, B.c, C.c, D.c. Their corresponding headers are A, B, C, and D.h. A.c includes these guys, B.c includes these. And so you can see here our program, it depends on all the O files, and then we're going to compile together all the O files. And then we're going to have a list of rules for each O file, how it gets created. So A.o depends on its .c file and all the H files it includes. So A.h, B.h, C.h. B.o depends on these. B.o depends on B.c, B.h, and D.h because B.c includes the B.h and D.h, and so on for the rest. Doing these make files by hand is hard to make sure that you specify the dependencies correctly and that you have everything up to date. So we're not using make. We're using CMake, right? And with CMake, you've seen that if we want to specify our dependencies, where are you? Right? We have this add executable line, and then we're like, hey, here's all my source files. And it takes care of all the dependencies for you. And it will generate a make file for you later on, and you can just use that make file. And as long as you don't edit your CMake list file, that make file will always be valid as long as you update your if you update your .c and .h's. So we will talk more about CMake files later on in next week's discussion. So stay tuned for that about what all this stuff does, because it looks complicated, I know, but it's a lot simpler than doing the make files. It's also, the C in CMake doesn't stand for the language C, it stands for cross-platform. So it helps you generate configuration files to work on everybody's computer, not just your own. Whereas a make file might only work on a Linux system. Okay. So over here we have an example program that's actually somewhat large. In this program, what we're doing is we are playing the game of tic-tac-toe, right? Which shouldn't seem too bad. And if you've ever had a class with me, we've done tic-tac-toe before in the past. We don't have as much time to spend on it as I would like to today, so instead of having you guys write it line by line, we're just going to go through what previous class has done. One of the things that you want to do when you're defining your problem is, again, break it down into sub-steps. Don't even think about coding first, right? Forget that you even know how to program when you're trying to solve the problem. And specify in English, or whatever your native language is, what are the steps are that you want to take to solve the problem, step by step by step. Think at a very high level, and each of your high-level tasks is probably going to become a function. You should also listen to yourself if you ever say like the word like if, or for each of these things, or I want to do this until this happens, right? Each of those things is going to prompt you to be what kind of construct you want to use in your program. Like, say if, you probably want an if statement. You say for each, probably a for loop. If you say I want to do something until, it's a while loop. So this is going to help you like break things up and think better instead of doing it all at once. For example, like if we think about the read lines problem, which you guys are all probably very interested in, you might say, you know, for each line in the file, add it to my list of lines. Great, that solves the problem, right? And we don't have to get into the details. But notice in that solution to the problem, we came up with more subproblems, like how do I read a single line from the file? And if I get that, I'm pretty much good as long as I also know how to append something to the end of a list. Does that make sense? And this takes time and takes practice to train this way, but try not to get bogged down in the details about allocating memory or what types you're going to be using. Approach those problems when you need to, but don't focus on them. So here, if I had to describe how to play the game of tic-tac-toe, or pretty much any game, it would be first, set up the game. Makes sense, right? Then, after you set up the game, what should you do? Well, we've set up the game, right? The game's there. It's good. It's ready to play, right? In this case, like tic-tac-toe, that'd be like drawing out the board and figuring out who's going first. So the game's set up. So after the game is set up, think about what you've done with every other game you've played in real life. You set up your game of Monopoly. What'd you start doing? Started playing the game, right? Right? And we want to keep playing the game for how long? Until it's over, right? So while the game is not over, we need to go play the game, right? And so we now need to define a little bit more, what does playing the game mean? So how do you play the game? Again, you can think generic. Don't even think about tic-tac-toe. Right? Like you get somebody's move, right? You're like, hey, I want to make this move. Then you make that person's move, and then you change the turn. Right? The other thing that we also have to do, because we're like programming, is we also have to show them what the game looks like so they can actually make it. Right? So if you look here at my solution, right, we make the board and we choose the turn. That's setting up the game. While the game isn't over, we show them what the game looks like, we get a move from them, we make that move, and then we change the turn. Right? Notice how pretty much exactly what I said is more or less line by line the pieces of code I have here. This is how you want to be programming, using lots and lots of functions. Oh, and then, you know, after the game is over, we should probably say who won, right? And then we clean up, because we're good people. And we want to make sure to deallocate all the memory. Does that make sense? And so now we need to go figure out, like, well, what do we need to do for, like, setting up the board? And the other thing that we might need to think about, well, is, like, how are we going to represent the board? So a game of tic-tac-toe, what's your board going to be made up of? It's like the rows, the characters, right? It's like a 2D array of characters, right? And one thing that you might also need to know, because you see, is like, you know, how big is the board, right? So over here in board.h, I'm going to be using a struct to collect all the elements together that define the board, right? I have the board itself, the 2D array of characters, how many rows, how many columns, and the character that we're using for the blank character, which just happens to be a little caveat of this problem so I can see what's being displayed. Right? We also might want to think about things that we might be able to do with boards. We want to be able to make a board, print a board, clean up a board, and put a move on that board. Right? But even here, we shouldn't really think about what we need to do. We should, again, be thinking about here from main, oh, I want to make a board. I need to set up, right? So in making a board, I'm able to group together all my board functions. So making a board, well, I make a board, and then need to dynamically allocate the space for the characters on there. So I make space for the rows, the row pointers. Then I go through each one of those rows pointers, and I make space for the characters in that row. And then I fill it in with a blank character, and I make sure to initialize my number of rows, number of columns, blank character, and I get back the board. All right, so here you can also see an example of dynamically allocating a 2D array of characters. Questions here? Okay, hopefully it's like not seeming too crazy. So now we figured out how to make a board. And the next thing we might need to figure out, over back here in main, is if the game is over. So when is the game over? Well, the game is over if somebody wins the game or there's a tie, right? And again, you want to think at this level. So if we look over here and win, oh, hey, I won. The game is over if somebody won, or there's a tie, right? And you can already kind of see, like, winning, there's 3 different ways of winning, right? You can win horizontally, vertically, or diagonally. So our win function is you won horizontally, or did you win vertically, or did you win diagonally? Should all make sense, right? Then we can go and define for each one of these functions, like, well, what does it mean to detect a horizontal win, right? And again, if you forget the code that's being shown up on there, right, how would you describe there's a win horizontally? What do you need to do? You want to go through each row, right? And you want to see if all the characters are the same. And then we also have to add the caveat that they're all not the blank character as well, right? Because the computer would be like, oh, you start out the game, everything's the same character because it's empty. Oh, you won, great job, right? So we have to include that in there. And so what we're doing is we're going through each one of the rows, and then if that character in the first character in the row is the blank character, we're just going to skip that row, right? And then we're going to go through the elements of the row if it's not the first character is not blank and see if there's a match. If we've gotten 3 in a row, or however many we need to win, 3 is probably a bad idea here. One thing that we might want to include in our board is like how many pieces in a row do you need to win, right? And then so you can make it like you could extend your game instead of being like a 3x3 square. You could go like a 4x4, or 5x5, or 6x6, or any number by any number to play the game. And then otherwise we're going to break, right? If we don't have, if we get 3 in a row, we win. This else over here means we're only going to enter if there was not a match. Then we're going to break out of the loop because there's no point in checking any farther down the row if we've already found a match, right? Or if we found a mismatch. All the characters in the row won't be the same. And you can think that we could define like a diagonal win or a vertical win the same, right? We just go through each column if all the characters are the same. In one column, we have a win, right? For each column, if all the characters are the same, we have a win. Or diagonal, since there's only 2 diagonals, you can say like, well, is there a left diagonal win or a right diagonal win? Right? And most of the code even says that, hey, is there a left diagonal win or a right diagonal win? Break it down. And then we check those things. We also have a tie. The game is a tie if all the spaces are filled and nobody won, right? So like, oh, hey, if you won, no, there's no tie, right? Then if we didn't win, we should check to see that all the characters are the same, or all the characters are not blank, right? And we've finished checking that. And then we can declare a winner, which is just pretty easy about printing out who won. Hopefully this should make sense. And notice how our problem is already kind of big, but notice all this code related to winning is in win.c and in win.h, right? So I'm able to group all the code related to winning, right, into just one function, or the game being over into one function, or into not one function, into one file, right? So I have a bit more organization in my program right here. Some input validation stuff. Let's see. For move, go back to main. So we got game over taken care of. Printing the board, I think you guys know how to do that. Does anybody want to see printing the board? Sure. So where do you think printing the board is going to be? What file? Board, right? So board.h, and then we can click on these little arrows over here, and that's going to take us to the definition. So I print some little space to be used for the column header to make things match up. So I print out some values so that people are going to be able to enter an input. And I go through each one of my rows more or less, and I print out the character on the board, right? Notice that one of the things that's a little bit different and sometimes people have issues with is that our representation of the game and what we show to the player do not have to be the same thing. Right? Some people try doing this problem. They're like, okay, I need an array of characters, and I need to put spaces in there as well and move over the correct number of spaces I'm writing things. Like, oh God, no. It's too much, right? Our internal representation should just be the characters that are on the board, right? And if we need to make things look nicer, we can deal with that when we print it out and when we're displaying. And we don't have to worry about it until then. So this is printing the board. Any questions? Just go through each row, for each element in the row, print it out. And we also put a space in there too. For cleaning up the board, right, make sure that you go through each one of your rows and you free the corresponding element, and then you free the pointers, right? So free all the characters, and then free the character pointers. Second time. Then we also set to null, and we change some other things to be 0, so that in case we accidentally tried to reuse this board after it was destroyed, we would be able to find our value or find our errors a lot easier, because we set things to null and set things to 0. How many of you guys have started using the debugger? Good. For those of you who have not used the debugger, use it when things aren't working. It'll save you a lot of time. So we also need to be able to get a valid move, right? So getting a valid move is probably in move.c. And this should be pretty easy, right? We just prompt the user for a move. We attempt to read their move, and we need to keep doing this for as long as the move that they entered is not good, right? And so I can have some other function that defines what does it mean for a move to be valid, right? What's it need for a move to be valid? The user is entering an answer in a row column pair. What conditions have to hold on the user's input for it to be valid? Has to be within the array, right? They also have to like not enter garbage stuff like cat or dog or whatever. They actually have to enter a number, comma number, or number space number. There's one other thing. You have to play on a blank spot, right? You can't play on top of somebody else. So over here, for a move to be valid, well, it has to be valid format, right? Numbers, number, comma number, which we've done before in class. It has to be within the number of rows and within the number of columns on the board. And that place has to be blank, right? But notice by breaking our problem down into functions, it's making it pretty easy, right? Like, notice those of these functions like can fit on my screen even though I'm zoomed in a ton and have super large font. Code should be like that too, right? If your thing cannot fit on one screen, definitely do more functions. So functions are what make your life as a programmer a lot easier. After we've gotten the move, what should placing the move look like? Right, because the user told you, I want to play at 1-2 or 0-0 or you know 2-2. Yeah, just go to that spot and change it to the character, right? So if we go to place move, the board at move.row, move.column equals whatever the characters that you said to put there. And then move.h, we've also defined what a move is. They have to say what row and column do they want to play in, and then what's the piece that they're trying to put there. I've also defined an enum to say whose turn it is as well. And I didn't have a good place of putting this, so I just kind of threw it in here, which is kind of bad, but it's there. So player 1 turn is going to be 0, player 2 turn is going to be 1. And then changing the turn. This guy right here is called the ternary operator. I haven't shown it, but what's going to happen is it's going to evaluate this expression right here. If it's true, this it'll evaluate to the first value. Otherwise, it will evaluate to the value after the colon. So if player turn equals player 1, our new turn is going to be player 2. Otherwise, it's going to be player 1's turn. Any questions? Yeah. Oh, when to use the arrow and when to use the dot when you're accessing the struct's member. So when you're accessing the member of a struct, if you have an instance of the struct.member. If you have a pointer to the struct, pointer or struct arrow member. So pointers use arrows. The one time that you probably wouldn't use an arrow and you still had a pointer to a struct is if you had an array of those structs. Then it would be like struct at I, struct back at I. That type is going to be of just type struct.member. Anything else? So if I switched player 2 here and player 1 here, or I want to replace player 1 here with player 2 and then player 1 and or player 2 and player 1. So if you switched all player 1s on this line to player 2 and all player 2s to player 1, it would still work correctly. Because it's basically just trying to flip the turn. Right? You know, if it's my turn right now, it's going to become your turn next. Right? If the current turn is player 2's turn, then it needs to become player 1's turn. Otherwise, if it's not player 2's turn, it must be player 1's turn because we only have 2 players. So switch back to player 2. Anything else? So again, split your programs up. Use functions. I cannot stress that enough. It will make you a much better programmer. Also, think through how to solve your problems before you start coding. If you don't know how to solve the problem yet, don't start coding, right? Or at least have an overall decent idea of what you want to be doing. Because if you start coding while you're confused, your code will be confusing. And it'll be hard to understand and be very complicated and do a lot of extraneous things that it doesn't need to do. Because you weren't sure what you were trying to do when you were writing it. Okay. Accidentally, nope, not that one. So now we're almost done with C, but one of the things they asked us to do this quarter is to talk about, or to integrate a library into our class, and for our class, I've chosen curses. So how many of you guys have read the tutorial? If you haven't read the tutorial, read through it. Curses isn't that complicated, but it can seem kind of weird at the front. And you're also going to be experiencing a lot more pointer funness because we're going to have a lot of window pointers floating around. So curses is a library that allows you to write portable terminal-based programs. So anything inside the terminal window you've been working with, curses gives you full control over it and lets you state what's going to display when, instead of having to print out line by line by line by line. The basic interface is you have a 2D array of characters, and you write to this 2D array of characters, and then you say, hey, my screen looks good, show it on the screen, and it will show up there. So if you want to compile with curses, you're going to need to add these lines to your cmakelist.txt. The first one says that we want to use ncurses if it's available. Then we try to figure out where curses is at on the system. So make sure you have it installed first if you don't already. Then we add an executable. So we're creating our program, whatever the name of your program that you want to be. You list out all your sources. You list out all your sources like your .c and your .h files. And then this guy is a variable that was populated by the find package command. And this will say that I also want to use the curses library to make my program. Wait, this shouldn't be there. Not there. Typo. Then we say, so we go to build our executable, then we say we need to link in the curses libraries, so go link them in. And then we say we also want to add the include directories that where curses is at into our program. This is going to let you not have to specify the path to the curses, so you don't have to say like /system/define like library /curses.h. You can just say #include curses.h and it'll find it for you. So if you want to compile with curses, it's just #include ncurses.h. And again, we don't have to specify a big complicated path because of the target include directories on the CMake file. Some people have had issues with getting curses to work, and they had to use curses.h instead of ncurses. Stop by office hours if you're having that problem, and we'll take a little bit of a further look on your computer. So if you want to start a curses program, you say init screen. This pretty much has to be the very first curses thing that you do in your entire program. There are a handful of other things that you can do first, but we're not doing them. So this is the first one. Turns on curses. If you want to end curses, it's end window, and it'll bring you back into the normal terminal mode. If you only want to leave curses temporarily, you can save your current terminal state. You can end the curses mode, do whatever it is that you need to do, turn curses back on, and then refresh the screen will cause whatever you had saved earlier to show back up on the physical screen. Curses is also going to define some global variables. One is standard screen. This is kind of like standard in and standard out, but it's like the whole screen as one unit. And we'll talk later about how we can partition the whole screen up into little smaller sub-windows. Lines will be the number of rows that make up your program, and calls will be the number of columns that make up your program. Not make up the program, but make up the window, the overall screen. There are also a couple of options that you can turn on and off to help you control curses. One is echo. So if echo mode is enabled, whenever the user types something, it's going to show up on the screen. This is just like with the normal terminal right now, right? When you type, the characters appear on the screen. If you don't want that to happen, you can enable no echo, and when the user types something, it's not going to automatically appear on the screen. This can be really useful for games we're doing, because like if the user presses like A to move to the left, you probably don't want the A character to show up on the screen too. Right? You're like, oh, A means left, and move the person on the screen to the left by 1 unit, instead of adding the character A to the screen. There's also raw and C break. We're probably going to be using a lot of C break. And what this does is when the user enters input, the input will be made immediately available to your program. Right? Normally, when the user types something, what do they have to hit before you get that input? Enter, right? So now, as soon as the user presses the A key, you get the A key. As soon as they press D, you get D. As soon as they press the left arrow, you get the left arrow. The only difference between raw and C break is how they treat some of the command characters, like Control Z and Control C. Control Z means to put your program to sleep and stop running it temporarily right now. And Control C means kill the program. Raw disables the special meaning of the characters, and so you actually just like get Control Z and Control C in as characters, and you can choose what to do with them. In C break, you'll actually get the signal, which will cause your program to behave like normal, just go to sleep or die. If you want to end raw or C break and go back into cooked mode, which is again like your normal usage of the terminal, you type stuff, it appears. You have to wait to press enter before you're able to get input. No raw and no C break will end those modes. Questions so far? Okay. One other option is keypad, and you say keypad and you specify some window. For example, like STD screen would be for the standard screen. This is the pointer. If you choose to enable the keypad, you're going to be able to get special characters like the arrow keys, up, down, left, right. You can also get the function keys like F0, F1, F2 for function 1, function 2, function 3, etc. You'll also probably want to enable this because we want our games to be able to be controlled with the arrows. So if you want to have stuff appear to the screen, add chair or add ch will put a single character to the screen and move you over. Move add ch will cause you to move to some position on the screen and then put the character there. Add string writes a string. Add end string will write at most n characters to the string. Move add string moves you to the position, then prints the string. Move add n strings moves you to the position, then prints out at most n characters from the string. All these functions will perform wrapping, so if you hit the end of the line, they'll go down to the next line and continue writing. I'm not quite sure what happens if you get to the bottom right-hand corner, because I don't think it goes back up to the top. I think it just kind of like stays there. And so like if you had like a really long string and you tried writing it into the corner, I think just like the very last character would appear. They would keep trying to write to the same spot over and over and over again. And again, they will all also move the cursor. The cursor is like where you're writing to as they put the character in. So once you put stuff onto the screen and you want it to appear, you have to use refresh. If you don't call refresh, stuff is not going to show up. Because what's happening when you're actually adding characters is you're adding them to like an invisible virtual screen. And then when you say refresh, it says, hey, take that virtual screen and put its contents to the physical screen. I always forget to do this thing. I'm like, why is it not showing up? Because you didn't refresh. Any questions so far? Also, I should mention 0, 0 is the upper left-hand corner of the screen. So if you want to get input, it's get ch. That'll get you a single character from the user. Move get ch will allow you to go to the specified spot and then get input from the user. There's also like get string, which I didn't have time to finish these slides, but we're going to do something fun. So we had that tic-tac-toe program, right? We're now going to take that tic-tac-toe program, and instead of it looking like this, hold on one second. So like now, like when you want to play this game, you have to say like where you want to play. Like I want to play at like 2, 2. And then it prints out the screen with the updated stuff on it. Like, or I want to play like at 0, 1. These guys are bad at tic-tac-toe. Don't blame them. Right? And the character shows up. This looks not so nice, right? Wouldn't it be a lot nicer if we could like move the arrow keys around to have us control where we're at on the screen, right? And then you know, like press space bar or enter to have that character go onto that spot. That's what we want to do. Does that make sense? Do you have any questions before we get started trying to do this? Okay. So I tried, and I'm not sure why. I'm going to try one more time to see if it'll open. I don't want to mess with this one. Yes. Nope, 36B versus. And for some reason, this file is appearing blank, even though you can clearly see I'm in the exact same spot, and there's a program there that I want to open. And if I try to open it from here, it's like, hey, open folder as CLine project. And then nothing happens. So I think that just is an issue with it has an issue to do with like Google Docs and using the same folder. So we're just gonna, oh wait, I enabled version control. Oh. I guess those files were automatically added. Well, version control, git, branches. Please restart CLine. So when you're looking for help on curses, the tutorial I found is really good. That's how I learned it. You don't have to read everything to be able to use it. And then if you're ever interested in finding other things, you know, you can Google like curses or ncurses, and you can get a link to a particular like instructions like, hey, like these functions all add strings. Here's a list of everything in the curses. Whoa! So I guess we don't really have time to get into it. So we will use these last 4 minutes for you guys to ask questions about anything you want. Yes? Oh, so like you have, sometimes you have to do, like you have like a global variable or a, so what's going to happen is when you're just doing the object file itself, the partial compile, it's going to just assume that that will be provided later on, and the linker's job is the one that's responsible for finding it. So what's going to happen is when you go and you link all the object files together with your later call to GCC, GCC is going to look up and it's going to be like, oh, hey, you tried to call this function. I didn't know where it was at before. Does somebody else describe where it's at? And it will go and fill in the link there. As long as you're making sure to include the header files, that's fine. The more complicated thing is if you want to share global variables across multiple files. If you wanted to share like global variables across multiple files, you declare it once in one file in the .c file, and you have to declare it as extern in the .h. And that lets the other programs know that we're only going to be talking about one instance of that variable, and we're going to need to find it later on. Anything else? Homework? Anything? Yeah. There is discussion this week. right? And discussion is not in the room that it was before chemistry. I think it's like right next to us.
Yeah.
In Hutchinson something or another. Yeah, 115 sounds right. 115. So right next door to us. I will see you guys on Monday. We will finish talking about curses on Monday, fingers crossed. And then Wednesday, we'll get into C++.